For centuries, it has loomed as a sleeping giant, a force of nature both awe-inspiring and terrifying. But now, the largest volcano on Earth has finally erupted, and the aftermath is more devastating than anyone could have imagined. The explosion was so powerful that it cracked open the Earth itself, unleashing chaos and destruction on an unimaginable scale. What caused this catastrophic eruption? And what does it mean for the future of our planet? The answers are as chilling as the event itself. This could be the disaster we've always feared. A volcanic frontier in the South Pacific. Tucked away in the South Pacific lies the island nation of Tonga, a small but geologically restless spot perched at the edge of the Tonga Kermadec Trench. This trench forms one of Earth's most active subduction zones, where tectonic plates meet and force molten rock upward. Many volcanoes in this area lurk beneath the waves, out of sight, scattered across remote arcs. Few people think much about what simmers below unless a major event breaks the surface. Yet in January 2022, the Tonga Ha'apai volcano burst through that facade of oceanic calm, unleashing an eruption that disrupted beliefs about how explosive undersea volcanoes can be. Before that dramatic day, the Tonga Ha'apai site was known mainly to local observers and a handful of volcanologists who had seen it sputter at times. Far from bustling ports or major cities, it was overlooked as long as it posed no immediate threat. Life in Tonga revolves around fishing, farming, and connections between scattered islands. Funding for advanced scientific instruments is scarce. As a result, continuous monitoring networks are limited. The region's countless undersea mountains often go uncharted, since large-scale mapping cruises require research vessels that smaller nations cannot always deploy on a whim. This lack of close oversight is not unique to Tonga. Several other island arcs face similar issues. Some host volcanoes that break the surface as small, uninhabited islets. Others remain fully submerged, only revealing their existence when drifting pumice or unusual seismic signals emerge. Experts occasionally discuss how these volcanoes might produce hazards, stealthy threats in the depths, ready to stir up tsunamis or stir giant ash plumes. Still, the scientific community had yet to witness a submarine eruption as forceful as what Tonga Ha'apai produced in January 2022. The realization that an undersea volcano could inject water to the upper atmosphere, spawn record-setting lightning storms, and send shockwaves around the globe changed how experts view submarine risk. Scientists now acknowledge that Tonga's watery terrain can mask incredibly volatile conditions below. What was an occasional curiosity to the international media became front-page news, especially once images of a towering mushroom cloud spread worldwide. For Tonga's communities, it was both a moment of awe and a harsh reminder that the ocean, despite its serenity, can hide enormous geological forces ready to strike without long warning. Challenges of submarine surveillance. Keeping an eye on volcanoes that lie under the ocean is no simple task. Researchers rely on an array of methods: seismic readings, hydrophone networks, satellite observations, and the occasional direct survey by specialized vessels. Such work demands time, money, and the right expertise. Even on land, building a robust network of seismometers and cameras can be tricky. On a remote island chain with limited infrastructure, the task becomes more daunting. Funding constraints often prevent small nations from building multi-station networks that track seismic activity with precision. For instance, to triangulate the source of tremors, stations need to be spaced strategically. That can be difficult on small islands that are spread far apart. Undersea detection also benefits from hydrophones that pick up vibrations traveling through the water, but positioning them in remote oceanic stretches is expensive. Their maintenance can require lengthy ship expeditions that local agencies cannot always afford. The matter of staffing is another hurdle. Tonga's overall population is comparable to a modest town in larger countries, so the pool of trained geologists or technicians is limited. Outside aid might come from organizations such as the USGS Volcano Disaster Assistance Program, but that help is often project-specific. Once the immediate crisis passes, limited resources may stall the upkeep of newly placed sensors. According to those involved in these efforts, the operating costs of advanced seismic arrays and underwater acoustic systems can strain national budgets. Additionally, new technology, like autonomous vessels or improved ocean drones, may not work reliably in rough seas or near active vents that release dangerous gases. Prior to the Tonga Ha'apai event, only a handful of undersea volcanoes had anything approaching real-time surveillance. One is the axial seamount off Oregon, monitored consistently since the 1970s. Another is Kikum-Jenny near Grenada, known for continuous mild outbursts. Yet many others in the Tonga Arc, the Mariana Arc, and the rest of the Pacific remain largely unstudied. Researchers know they exist from bathymetric maps or from occasional bursts of activity. Still, no round-the-clock data stream exists for most of them. That gap loomed large when the Tonga Ha'apai volcano suddenly revved to extremes. Although satellites captured the eruption's dramatic cloud, the local vantage points were limited. No dense grid of sensors was on hand to watch every microquake or creeping change in gas composition. As a result, the final days and hours leading up to the colossal blast remain only partially understood, pieced together after the fact through patchy observations and retrospective analysis. Early signs and surging tensions. By late December 2021, scientists and Tongan observers noted that Tonga Ha'apai was stirring again, releasing steady ash plumes and bursts of steam. This wasn't unprecedented. Throughout the last decade, the volcano had shown occasional signs of life. Sometimes, these smaller eruptions even built short-lived land bridges between the twin islands of Tonga and Ha'apai, piecing together fresh rock above the surface. In many cases, waves eroded that new land within weeks or months. Because these episodes were usually modest, no one expected a doomsday scenario. The caldera, around 200 meters below the sea's surface, was known to produce steaming vents. Yet the overall pattern seldom seemed like it would escalate into a planet-wide spectacle. Local officials noticed that more ash was falling than usual, but in the island's experience, such buildup could occur with moderate submarine eruptions. Then something changed in early January 2022. The internal system grew more restless. Magma and inflicted gases began to push upward. Cracks opened, possibly allowing more water to mingle with scalding rock. At the same time, there might have been chemical processes at play. Pockets of magma with slightly different compositions can spark more vigorous gas release when they merge. According to research from volcanologists like Shane Cronin at the University of Auckland, such interactions can dramatically boost internal pressure, setting the stage for a runaway furnace if conditions line up just right. Without detailed sensors, scientists couldn't confirm the exact moment when conditions reached a tipping point. But in the days leading to January 15th, satellite imagery revealed a growing cloud of ash that was larger and darker than normal. A few minor jolts appeared on regional seismic networks, though they were overshadowed by constant micro-tremors that submarine eruptions often generate. For many Tongan residents, the buildup was ominous, but not yet alarming. An undersea volcano over 60 kilometers north of the main island didn't pose an obvious immediate threat. Only in hindsight did experts realize the cocktail of high-pressure magma, abundant gases, and infiltration of seawater was about to yield a volcanic storm beyond typical undersea events. Days later, the world would see an eruption that blasted water molecules into the upper atmosphere fast enough to absorb far ultraviolet light, a feat never clearly observed before on Earth. The Big Blast, January 15th, 2022. On that fateful Saturday, everything escalated. A tremendous explosion shook the seafloor, launching ash, gases, and superheated water high above the South Pacific. Satellite images captured a mushroom-shaped cloud that sprawled across hundreds of kilometers. People as far away as Fiji reported hearing sonic booms. In Tonga, the eruption's roar was deafening, rattling windows and fraying nerves. In Baltimore, Maryland, Larry Paxton was scanning the edge of space with sensors designed to detect phenomena in the far ultraviolet band. He spotted an unexpected dull region about the size of Montana. It turned out that water molecules were blocking or absorbing these specific wavelengths of light. The source? Water hurled so high and so fast that it lingered in atmospheric layers not typically reached by moisture from volcanoes. Paxton's team calculated that the amount of water could fill roughly 100 Olympic swimming pools. Even more staggering was that these molecules had traveled at speeds exceeding the speed of sound somewhere along their journey. Down at sea level, the volcano vented repeated blasts. Observers described thick, inky ash plumes spiking the sky. Lightning storms raged within the column, fueled by collisions among ash, ice, and water droplets. Scientists later deemed this the largest concentration of volcanic lightning ever monitored, reflecting the extraordinary charge buildup from so much moisture and material. Then came a sonic boom that traveled around the globe, possibly more than once. Meteorological stations in distant countries picked up abrupt pressure changes. People in Alaska noticed a spike on barometers roughly after the wave spun halfway around Earth. That same eruption triggered tsunamis in Tonga and beyond. Local coastlines were battered by surging water, ripping away boats and damaging homes. The country's main island saw ash drifting onto runways, delaying relief efforts. Farther afield, places like Peru experienced unexpected wave activity, causing incidents at coastal facilities. The fact that one undersea volcanic site, a small point in the vast ocean, could generate ocean-wide ripples shocked many tsunami experts. It wasn't an earthquake, nor was it a simple partial collapse of an island flank. This was a direct outcome of explosive force. Scientists worldwide scrambled to understand and measure what they were witnessing. While short bursts of submarine eruptions are not new, the scale here was off the charts. By day's end, it was clear that the Hunga Tonga Hunga Ha'apai event belonged in a category of its own, illustrating how certain depth conditions could turn a seemingly moderate eruption into a near unthinkable behemoth. Inside the eruption's mechanics. In the weeks that followed, volcanologists worked overtime to piece together how so much energy erupted in such a brief window. Shane Cronin explained that the volcano was likely in a stable eruptive state for about a month, releasing moderate ash and gas. But signs point to a hidden merger of magma sources with slightly different chemical traits. When these magmas mixed, volatile gases dissolved within them could have been released more aggressively. Seawater flowing into cracks near the vent provided the final push. At 200 meters of depth, there is enough water pressure to keep the system under tension, but not so much that it clamps everything shut. Once a crack let seawater meet scorching magma, it rapidly turned to steam. That steam multiplied the explosive force, leading to the supersonic ejection that Paxton's team indirectly observed through the far ultraviolet data. Trillions of tons of debris and ash soared upward, and a giant void was left behind within the caldera. Cronin and others suspect that water rushing back into this massive hole also spiked the tsunami waves. Typically, major tsunami events tied to volcanoes come from the collapse of a caldera wall. But here, it appears that water surging into newly emptied space contributed to extra wave energy. It was reminiscent of dropping a giant stone into a pond, except on a scale measuring kilometers, not meters. Another aspect that raised eyebrows was the record-high concentration of lightning. The volcano's wet, ash-laden column churned a stew of charged particles. This chaotic environment produced more lightning strokes than seen in typical volcanic plumes. Some satellites captured the spectacle, noting tens of thousands of lightning flashes during the most active hours. It was quite unlike the calmer displays from purely magmatic surges on land. Sharon Walker, an oceanographer at the Pacific Marine Environmental Laboratory, pointed out that investigating these processes up close is tricky, since approaching an active caldera can be dangerous. The combination of gas bubbles, scalding water, and persistent instability deters large research ships. Some smaller missions went out in the months after the blast, but a full mapping expedition is expensive and requires well-trained crews. Even so, the pieces that scientists have collected suggest Tonga Ha'apai was prepped for an eruption of extreme magnitude. If one slight factor had differed, the blast might have been far less powerful, or perhaps even more so. Shockwaves and tsunamis. For days and weeks after January 15th, the planet felt echoes of this underwater juggernaut. Pressure waves circled Earth, registering on barographs in countries many thousands of kilometers away. Some people reported hearing faint booms at distances that seemed improbable. The eruption's energies spanned not only the ocean, but the atmosphere as well, setting this event apart from classic land-based blasts. Tsunamis from the eruption carved a path across the Pacific Ocean, though most places experienced only modest rises or strong currents. In Tonga, the damage was serious. Low-lying islands faced inundation, and farmland was inundated by salty water. Farther off, regions like Peru saw enough wave force to disrupt coastal refineries, causing environmental issues. Observers were astonished that a volcano perched on a small dot in the Pacific, as some put it, could stir up ocean-wide surges. Historically, large regional tsunamis are often earthquake-driven along major fault lines. This time, a single volcano proved it could create a transoceanic hazard under the right conditions. Emily Lane, a tsunami specialist at New Zealand's NIWA, analyzed how the waves traveled so far with surprising coherence. Part of it might be that the explosive pulse gave the waves a strong initial push. Another possibility is that the atmospheric shockwave played a subtle role, adding energy at crucial moments. In effect, the volcano's blast was so intense that it jostled the atmosphere, which in turn may have nudged or reinforced wave motion at some points. News of the tsunami's reach spurred renewed calls for expanding tsunami warning systems to account for volcanic causes. Many standard algorithms focus on large seismic events as triggers. But as Tonga Ha'apai demonstrated, a robust undersea eruption can produce waves that fill the ocean basin. Lane and others argue that an eruption-based tsunami might behave somewhat differently, so calibrating warning thresholds to these possibilities could improve future alerts. On the atmospheric side, names like Olar Verl at the National Center for Atmospheric Research came forward to highlight the unusual wave patterns that soared into the ionosphere. There, water vapor might have minor but notable effects on local temperature or cloud formation. The notion that an underwater volcano could feed moisture to such lofty altitudes was borderline unimaginable to many meteorologists. Yet Paxton's far ultraviolet anomaly was plain evidence that real Earth processes can rival science fiction scenarios when the conditions align.